Well, good morning. My name is Richard Campbell, and I'm going to not only do the opening talk, I'm going to do the opening. So welcome to the conference. Who's been here for the first time? Oh, wow, a few hands. But that means there's a lot of folks who've been here before. This is my first chance to be in Iași. I've been in Romania before, but this is the first time since the pandemic to be back, and I'm here because Irina asked me nicely if I would come, but her voice is a bit shot right now, so I'm going to do a little bit of the housekeeping as well. I hope you've obviously all made your way here. The Wi-Fi passwords on the post here and there, it's Agora at 2019. And the most important thing we can ask you for is your feedback. This show is made by you. And without your feedback telling us what sessions you want, what people you want to see, we don't know what to do. So if you take your time, take a little time, fill in those forms, let us know what's going on, we'll keep making a better show for you. Thanks. As I said, my name is Richard Campbell. I've been making software for a really long time. I'm known for making podcasts. Any .NET Rocks listeners? Oh, wow, a few hands there. Thank you. Thanks very much. My friend Carl Franklin started the show .NET Rocks back in 2002, so he predates the word podcast by a few years. I'm the new guy. I came on board in 2005. We're at show 100, and we published yesterday episode 1894. So we've made a few of them. Talked to all the luminaries in the .NET industry. It's really for .NET developers, so if you build software, we've got a conversation going on. They're free to download, free to listen to. I also make, because I live in both worlds, both on the sysadmin side as the developer side, I make a show called Run As Radio, which I've been doing since April of 2007, because making an sysadmin podcast when Vista just shipped seemed like a good idea. So 928 episodes of that. And for a brief interval, we made a show called The Tablet Show as well, because we weren't sure what to do with tablet stuff. It was all new then, and so we did that for a couple of years, and then we rolled it back into .NET Rocks. But that's not what we're going to talk about today. I'm quoting Bill Gates here, although he was quoting someone else. When we start talking about the future, this idea that we often want results faster than we can really get them, that what we do in the first couple of years of a new technology rarely amounts to very much. It takes longer than that. You have to work harder at that, because after 10 years, it's extraordinary what's happened. This quote's often attributed to Bill, but he even admits that he was quoting a guy named Ray Amara, who was one of the original computer scientists from the Stanford Computing Facility in California, who passed away back in the early 2000s, but was really one of the thinkers that helped shape our industry from the very beginning, as did Bill. And then one of my examples of this truth is the cloud. For many years, we talked a lot about the cloud. We didn't do a lot with it, but by 2024 now, the cloud has permeated a lot of what we do. We have changed the way we build software. It has been long enough now, and it's been incorporated that we're thinking more broadly about what software even looks like. The architecture has changed. We talk about being cloud native. And we have essentially an on-demand computing resource for ourselves that you pay for by the minute, and that shapes the way you want to build software. We've put supercomputers into pretty much everyone's hands now. Everyone has a smartphone for the most part. This is the most popular computing device in the world. I mean, what's more personal than a computer you keep so close to you? You're afraid it's giving you cancer. So, and the combination of cloud and phone means we're producing tremendous amounts of data. We're largely not protecting this data sufficiently. Hopefully the EU continues to lead the way on that. But these are just trends. We have ongoing processes that are making more data with more devices and more cloud all the time. None of this is particularly innovative. But if we're really going to think about the next decade, we've got to think about what's going to change, what's really going to impact us going forward. So let's talk about another pioneer of the industry, Gordon Moore. So Gordon Moore was one of the fellows that formed Intel and built the first microcomputers, the first microprocessors. And initially, they were making RAM. They didn't make the first CPU till the 1970s. But in the 60s, after the Apollo program, when the Americans went to the moon, they were using core RAM. They literally had meshes of copper wire with little ferrous cores, and that's how you stored bits. You know, a byte was about this big. Not a real efficient way to go do things. And so making RAM out of silicon was a big deal. And Gordon had noticed that roughly every 18 months, for the same amount of money, he could double the number of transistors on a die and increase the amount of RAM. Now, he didn't call it a law, because it's not a law. It's a effort, but it's an observation of industry. When a group of people work really hard, that they could double the density of transistors every 18 months to 2 years. And this trend has continued. This is a graph of CPU designs from the Intel 4004, just in the early 1970s, up till the mid-2000s. The number of transistors has gone up exponentially. And it makes a pretty good line. And it's only because I have this exponential function on the left side, right? I'm adding zeros like crazy to keep that line straight. If I did a normal geometric progression, you get a hockey stick, kind of a useless graph. Now, these are not fun things to look at. Here's how I explain it to regular humans. What's this? Warp core from the Starship Enterprise? No, that's this. This is a Cray XMP supercomputer, circa 1985. Only about 100 of these were built. These were the highest performance computers on the planet at the time. They modeled weather systems, they computed the great trajectories for satellites going across the solar system. It consumed about 200 kilowatts of power. To keep it from melting down, all of the circuit boards are actually in mineral oil, and they're pumping mineral oil for the cooling for it, and it put out a whole 1.9 gigaflops of processing power. So 1.9 billion floating point operations per second in 1985. And you can compare this with the iPad 2. So now it's 2011. It's 26 years later, and for about $800 US, you can get 1.9 gigaflops that you can play Candy Crush on, or give to children. So what was the highest performance supercomputer in the world is now a consumer device in a little over a generation, 26 years. And let's face it, that's 2011. This is not fast. When we talk about fast consumer compute devices today, generally you look at video cards, right? The NVIDIA's RTX 4090 running around $1,200 US, 16,000 cores on it, pulls down 82 teraflops. So 40,000 times faster than that iPad 2 or that Cray XMP. And it's a consumer device. It also consumes about 400 watts, so about twice what your CPU is going to consume, so I hope you got good cooling. The fastest computers in the world right now are supercomputers. So number one, there's been a race between the Chinese, the Japanese, and the Americans building larger and larger supercomputers. It's called the exaflop race. And the Americans have achieved it. Actually, a couple of years ago with this machine, the Frontier supercomputer, covers about an acre and a half. $600 million, 21 megawatts of power, so bring your own nuclear power plant. And 1.1 exaflops, so 1,100 petaflops, although they've got a new version coming, it'll be 2 exaflops. So that's 14,000 times faster than that 4090, or about 600 million times faster than the iPad 2. Yes, there's only one of these, but then how many do you need? There's only so many computing problems that need this kind of supercomputing performance. Right? They do a lot of flow modeling with this and weather prediction. That's kind of all it's for. And yet, Moore's law is ending. We're getting down to the line. We have a high watermark. You know, I showed you a supercomputer from the 1980s and then showed you an equivalent consumer device. Now I've shown you a supercomputer from the 2020s. Is that eventually going to be a consumer device? It's an interesting question. Like, how much compute do you really need? How fast does Candy Crush need to run? We can't keep on this graph. We're starting to taper off, and it's taking longer to make higher density chips. They're just a bit too close together. So now we're down. This is an electron tunneling microscope image of the 5 nanometer process that IBM perfected to make transistors about that size. I actually like this image better. This is scanning tunneling microscopy. So this is actually looking across the surface of the substrate inside of a chip. The yellow bumps are silicon atoms. The blue holes are the boron to make it a semiconductor. Each one of those silicon atoms is 111 picometers across, or 0.1 nanometers. So when we talk about 5 nanometer and 3 nanometer process, like, you're getting down to the dozens of atoms. That's just not enough atoms. Now we're getting very clever. We're trying these different structures and ways to try and manage that, but we are getting down to a number of atoms. Now this is not necessarily a bad thing. We kind of traded on for many years on the fact that every few years we would get more computing power for the same amount of money. But it actually hasn't been true for quite some time. The yield on the new machines has just not been substantial enough. Once upon a time, you bought your computer because it had a certain number of megahertz in it or gigahertz in it. Anybody know what the clock speed is on an iPad? They don't advertise it. It's not a thing. It's not a way to market anymore. Sufficient would be the better description. Like fast enough. We have other constraints that are more important. And the big issue here is that, in some ways, Moore's law has held us back from making other improvements. As long as you had a faster computer coming because a group of engineers busted their butt to build denser and denser chips over time, you didn't have to make other optimizations. That's why Intel still fundamentally sells the same x86 chip. The same original 63 instructions that were in the 8086 are in the current versions of the i7s and i9s. They've kept that architecture going. They've kept adding to it. There's a downside to that. Today, the Intel architecture is layers and layers of different bits to try and maintain that backward integrity while still getting modern performance. And this is one of the areas where you can optimize, because now look at the architecture of an ARM processor, because it doesn't have that legacy. And so they've simplified the structures a lot. And so for the same amount of energy, they can compute more efficiently. And you're starting to see this come true in the form of what Apple's done with the M1 and the M2 and the M3, where they're emulating x86 instructions almost faster than the native hardware can run it. More importantly, they've done mass integration on this chip. So once upon a time, I had a CPU here. There used to be a separate math processor, too, if you're old enough. And then we probably have a GPU and a card somewhere. Today, all on the same chip is the CPU, a big GPU, an NPU. The M3 Max is 16 cores plus a 10-core GPU plus a 16-core neural net that puts it up about 18 tops, which is pretty good. It could be faster. There's 25 billion transistors in that package for a few $100s, about the same price still. So rather than, that's pretty high density. The 3 is up to about 3 nanometers. It's about as small as we're going to get. But they've tightened the package up to get more performance on it. So we're finding a performance other ways. Simpler architectures, closer coupling, to continue this trend to some degree. Make some really beautiful computers. You're also going to see ARM now starting to appear in the data center for that same reason, just more efficient. When Microsoft coupled themselves more to the cloud rather than to Windows, very quickly, the majority of workloads inside of Azure became Linux. And the fact that .NET revamped itself to run just as fine on Linux as it does on Windows meant that a lot of developers learned if you switch over to the Linux version of .NET when you push out your app into production, you cut about 20% off your price. You know, the fact that we're now paying for cloud by the minute, and so how our code is written actually sets how much it's going to cost. And what gear it runs on matters. We're finding a mindset from different kinds of optimizations. This has only emerged in the past few years, and you can see it's going to continue. The folks at Microsoft are optimizing their code for this massive scale because they are charging you a flat rate for a lot of it. And so the more efficient they can get at it, less money it costs them, the more they make. And I don't know if you noticed, but Microsoft's making a lot of money right now. There was a bit of a scandal about they were rewriting some C# services in Rust. And that was just an opportunity to save money for them. That Rust is a great language for that kind of optimization. I wonder if in the next few years, it's just not going to be a part of our normal job is to, as we write code, be assessed on how much that code's going to cost to run on the cloud. So can you make a more performant version? That performance tuning will have a direct return because you can reduce the cost of operations for it. And speaking of languages, we got lots of them, right? You remember Python, the great beginner language, big on data science. JavaScript, obviously around a lot of places. Our friend Java, writing in the enterprise, which of course is its cousin C#, although somewhat evolved now, open source, cross-platform, like Java always was. You know, Java's tagline in the beginning was, any platform, one language. .NET's original tagline was, any language, one platform. It's not true anymore. And I'd be remiss not to talk about C++, just as still the powerhouse language that a lot of stuff is written in. So these are our standby languages, and there's a reason we have an array of them. They all represent somewhat different skill sets. Some of them have historical references. I mean, Microsoft resisted the truth that C# was just their Java alternative. But I've been working on the history of .NET for some time now. I'm here to tell you that's what it was. They also took the second mover's advantage. They saw the mistakes that Java made around type systems and did a bit of version. They incorporated generics from the very beginning, so they have a bunch of advantages. Not that I want to pick on Java anyway. Living under Oracle's umbrella is enough punishment for anybody. But think about more contemporary languages, things like Kotlin, modernizing the way we do Android development, and Swift, same for iOS and Mac OS. Go as a truly cloud-native language. And of course, Rust, which I've already mentioned. And I'll throw TypeScript in there too as an extension onto making more maintainable JavaScript. Why so many languages? Look, I only did 10. I bet you could name 10 more. There's lots of them. We feel around for better ways to express the work that we're being asked to do against the systems that we have to work from. We don't develop in a bubble. The hardware we run matters. What the customer needs matters. These are all these pieces that come into play, and sometimes an option is to switch languages. And it's one of the things I think that's incumbent upon us as developers today is don't be dedicated too much to a given language. There are opportunities there, but recognize that a language choice is more than just your ability to express work in that. It's also how well your teammates will be able to do it as well, how maintainable that's going to be long term. Can you hire more people in that space? You know, there are very hip new languages coming up right now, but you can't find someone with 10 years experience in it. Okay. This does lead us to a conversation about web, because for better or worse, there is no sign of the browser not continuing to be the principal client interface. Why? Well, it exists as a security context already on almost every device. There's virtually nothing shipped today that doesn't have some kind of browser in it. So there goes your deployment problems, always running on the current version. Sometimes these different browser makers battle a bit, so running the latest bits gets to be problematic, but you know, we find some safe spots to work there. And the fact that we have this diversity of libraries speaks to the fact that there isn't one right way to do things, that how you like to develop is a justification for a tool set too. These represent different styles in how we write code and how we build maintainable systems. And I could update this slide every few months with another JavaScript library. I mean, I think the cadence is finally slowing down as we're starting to get to a pretty functional state. I think the progressive web app is an important part of all of this, that we've tried to add more client-like features to browsers. Now, that doesn't mean anybody is using PWA fully. I don't think you can. At the minimum, you gave yourself an icon on a phone, right? It's a manifest so that the typical user doesn't realize that it's a web app, not just another icon on their phone. And hopefully you're doing more with that, dealing with some disconnected states, some caching capabilities. You know, there's a lot to be done there. But that's pretty much leveled off. And I think even more relevantly, with our friend Steve Sanderson taking advantage of WebAssembly to bring us versions of .NET that ran inside of the browser, but also the Golang team has done that now too. If you don't want to work in JavaScript, but you do need to work in the browser, you can. That we now have a way to put the code we like to write into the context of the browser. This is one of those things that you can see is just going to persist because it's good enough. It's done the hard thing. It's already on all the devices. So it's not going to go away. And if we're going to talk about Sanderson, we can talk a little bit about Blazor. This was a product that I think Microsoft almost didn't want to ship. You know, Steve did it himself. He ran with WebAssembly in a weird version of .NET and got it running in about 2016 and scared everybody. And Microsoft kind of left it in the beta pool for a long time. Because Microsoft's culture was to come in second for a lot of things. They didn't want to be first. They didn't want to be the ones who threatened JavaScript. They waited until Golang shipped first in WebAssembly, and then they pushed out this thing and have been off with the races. But for a lot of .NET developers, this was a return to something we knew. And to me, as someone who gets to be a part of the community for a long time and talk to a lot of folks, it was a reminder of how much influence culture and history has on the way you write software. The developers that love writing Blazor are also the ones who came from web forms. Tools they recognized, patterns they were comfortable with, a language they knew. And the fact that we could put it into a new context to have it run server-side or client-side, that we could take advantage of modern browser features without having to go whole hog into JavaScript. Compelling. And it speaks to things that we're going to see in the next 10 years, that we're going to continue to protect the patterns of what people know how to do. Same is happening with .NET. .NET has turned 20 in 2022, so it's 22 years old now. It can drive, it can drink in America. And Microsoft, of course, has completely transformed .NET. .NET once upon a time was a tool for selling Windows licenses, right? It was an enterprise development tool. It was our alternative to Java so that they could sell more Windows. And eventually that became less important in the middle aughts and early 2010s. And they realized that, no, we needed to be a cloud company rather than a Windows company. The .NET team said, we want to transform .NET into cross-platform, open source. We don't care what the operating system is, just a place to write code. And they were able to pull it off. And then it's really settled in by 22 with .NET 7. They've also changed the licensing approach to it, where the version 7 is going to go out of support like next couple of months, because 8's the long-term support. Long-term support is now 3 years. 9 will be another short support one. But they're trying to get us to iterate. And that speaks to a change in pattern of software. The security concerns that we have today are much more serious than they ever were before. The black hats know how to make money now, and they take advantages of weaknesses in software, and there are weaknesses in frameworks. And the only protection is to stay current. And so getting into patterns where we don't cling to long-term versions of anything, that we replace them constantly. I talk to Java folks who are in the same boat, happily still running Java 11. The current version is 20. So if there's a weakness there, you're at risk. And if you're not in the routine of replacing them, you've got vulnerabilities for that. I do think that Microsoft's trying hard to make the smart client happen. Their MAUI product is an approach to this, to try and find a way to build a uniform client. Now, it comes out of Xamarin Forms, so what it's really good at is building a uniform iOS and Android app. It doesn't build that good at Windows apps yet, which is weird, but okay, much less on Mac OS. But we have a need as developers to deal with the heterogeneous client world. Not that our customers actually care, they just care that it runs on their device. The fact that it has to run on all devices, not their problem, your problem. And we're trying to make that as painless as possible. And the fact, we know this is not a solved problem because you can see how many libraries there are. Right? Look at Uno and Avalonia. We've been exploring ways to try and build clients uniform across multiple devices, and they're just not good answers. And that's before we've actually shaken up the device. The laptop, the tablet, the phone, they've all been pretty consistent for quite some time now. A screen, typically a touch interface, maybe a mouse. What happens when real change comes? Because real change is coming. So this hasn't solved itself yet. It'll be interesting to see if it does. That's why the web thing's still winning for the most part. But now I think we sort of laid the land down. We can start talking about some newer things. If you haven't paid any attention to Power Platform or to all of these low-code solutions, a lot of folks look at this and go, well, it's not for developers. It's for domain experts. It's the 21st century version of Microsoft Access. I look at it as a better way to build clients. Because out of the box, by its nature, it'll drop on the phone and the tablet and the PC with a whole lot of effort. You can focus on your back-end parts. So we are talking about a hybridization of development where we have folks that are going to specialize in the client side using tools like this. And then if you're happy doing back-end work, it'll incorporate those back-end pieces. But there's an awful lot of plumbing that's already known. So if you're living in the cloud space, the data's already there. Connectors to a lot of apps that people already use, like Teams and SAP and Salesforce. And then still with room to do customizations. We're not like any of us were ever getting to the bottom of our to-do lists, right? There was way too many things to build. And this also is an emerging technology because there's a dozen of these. Power Platform is just Microsoft's implementation, but Oracle has one, Salesforce has one. Everybody's feeling around for a way to move forward on this, to be cloud native, built from the cloud from the outset. Back on the smart client side, we're still fighting with containers to try and keep those old apps alive, different ways of encapsulating badly behaved software. I would hope that this goes away. It's just that the experience over the past decades is that it won't. Most software can be modernized and runs in safer contexts and so forth, but it's like every user has one badly behaved piece of software, and we're trying to find ways to contain those so that they don't have to give them up, but they don't risk the whole system. All right. One last bit. I'm not going to talk a lot about Web3 because it makes me giggle. Web3 to me really comes down to three things: crypto, which we can definitely mock, blockchain, and decentralized web. We have had a wave of centralization. You know, the early Web 1 days, those late 90s through the dot-com boom, was very decentralized. People had web servers under their desks, which we quickly found out was a bad idea. And then we moved to a very centralized web, even before cloud, you know, the GeoCities model. But think about how many people just ran their site out of Facebook and gave all that data away. And so you're sort of seeing a push back the other way. Although it tends to be in the cloud, but in the cloud with an awful lot of autonomy and legal protection around it. Blockchain has this problem, the same problem that BitTorrent has, which is that its primary use was for a technology that has strong criminal connections. An awful lot of crypto is just money laundering. And so I don't know if this technology is ever really going to get a break because it's kind of tainted. That being said, most people don't actually need a decentralized data store. But it's an interesting technology, and I've seen a few good cases for it. All right, I'm going to get into weird stuff from here, but I want to talk a little bit about change, because there's different people in this room with different career choices. There's a sense that we always need to be on the leading edge, that we always have to take on the first bits, the latest bits that have just come out, try all the cool things, and it's simply not true. I've seen folks make a career of it, getting in on a new technology at the beginning of their career and just staying with that tech. So they go from the ascendant technology that's growing massively and more people involved in it, and into a descendant technology where there's still a lot of install base, a lot of software out there that still needs maintaining, but there's no new people coming into it anymore. And so there's fewer and fewer of them. Even if there's not a lot of new projects starting on it, there's still lots of stuff to maintain. Ask a COBOL developer how much they're making right now, because they're in their 70s and they cannot retire. There's nobody to replace them, and they're important. That's one end of the scale of a career approach. If you want to stay with a tech that you love, that a company cares about, you can do it. Just make sure you know what's going on around it and you're truly an expert in it. If you want to chase latest and greatest, you can do that too. There's lots of ways to have a great technology career. I know we're dealing with some layoffs and things right now, but for the most part, the demand for technology only grows. We're shaking out some things to try and do stuff right, and some new technologies are coming on the pipe that in the next 10 years are going to have substantial impact. So let's start with the one most people are thinking about, which is AI. Now, I pull up HAL 9000 for a reason. Artificial intelligence has a problem. It's an old term. It's from the 1950s. And it was a group of scientists trying to convince the US military to give them money. That's where they came up with the term. The first time the public ever heard the words artificial intelligence was in 2001: A Space Odyssey, where HAL tried to kill everybody. So we've set the stage for the expectations of what artificial intelligence means to the general public, and it kept happening. Terminator, all of the MCU, are you Jarvis or are you Ultron? And now we're going to call a set of real technologies artificial intelligence. Like, they've kind of created an umbrella term. I always look at it this way. If it's called artificial intelligence, it's because it doesn't work. Because as soon as it does work, it gets a new name. You know, those earliest technologies, the ones I was just describing with Marvin Minsky and them for the US military, that's that planning and schedule optimization tech. In the 1970s, we got after systems and robotics, all under the AI umbrella. This is the early speech systems from the 90s. And then we get translation and classification coming out of natural language processing in the aughts. And now the most modern stuff, deep learning, analytics, image recognition, they all get new names. Somebody says, I have AI tech. It's like, oh, you have stuff that doesn't work. How nice. Why would I pay for that? What is it really? It's a large language model. Okay, now we have something to talk about. Right? It's a usable technology. Now, there's lots of ways to use different technologies. Image recognition has its challenges. But for some software, it can be useful. My favorite. The software was right. Certainly we had a wave of chat bots. I think that's changing with the LLM, but it's an interesting area also in the machine learning space. One of the ones I don't think has been talked about much since LLMs have overwhelmed everything was that there was a team inside of Microsoft making the form recognizer. So what they were doing was taking existing workflows in a company that hadn't been automated, scanning the forms, and it would generate the pages for it. So combine this with Power Platform, you're pretty much having a thing that would rewrite apps. Like what if instead of scanning forms, I was scanning ASP pages? We have the bits and pieces. This is various places that machine learning drops into. And of course, go back to the data stuff, right? That once upon a time, this was a whole specialty, predictive analytics, where we had all these different computational models. I worked on this in the late 90s, and we would spend millions and years to plan out systems for how we were going to analyze corporate data to get value from. Then the cloud came along, and instead of trying to figure out which one of these complicated math models you needed to apply to the data, you pay them by the minute, just do them all, and then do another set to analyze which one got the best results. And so predictive analytics then got machine learning models added into it, and now we talk about things like prescriptive analytics, which you've probably experienced, where we now have software that is capable of presuming an action after an action occurs. You ever thrown a bunch of stuff into a shopping cart just to see how much it was, and then threw to close the page, and an hour later you got an email saying, "Hey, if you'd like to buy that, I'll give you 10% off." And there's no person involved in that, right? That's all data analytics software that says I'm trying to tickle you to actually go further down the sales pipeline. And so we're getting better and better systems around these machine learning models. And it's not just e-commerce, which granted I've done a lot of, but I saw systems that GE was doing for power turbines, estimating when was the best time to replace one. Because you'd think it's just when the business is slowest, but it's also when they have most redundancy, what's the risk for failure that would cause other problems. So machine learning models come into play for all of that. But let's talk about the original LLM. Well, there was a couple before that, but the first product that a lot of us saw in the Microsoft world was Copilot. And that's fine. Copilot was built on originally GPT-3, then 3.5. Certainly a powerful tool. And it was trained against a data set that GitHub had access to, which was all this public code. And in a lot of ways, this was the perfect code. It's a great name, which is why it wasn't invented by Microsoft, right? It was the GitHub folks that came up with that name. Then Microsoft's smart enough to go, Copilot's a good name. We should use that everywhere. Because what does it say? It says, it's still your fault. It's just the Copilot. You're the pilot. But also that we could fetch some, this leveled up Stack Overflow in a big way. It did let us to grab more code, and they've continued to evolve it. We're an ideal customer base for a tool like this, because we are pretty educated. We're used to studying code and saying, what does this really do? And, is this my intent? And obviously the compiler gets a say. So, and this is now mature enough that I'm talking to PMs who are talking about their whole team being 20, 30% more productive, checking in more code with less repair, and actually having a good time with it. Like, it's a pretty compelling tool. And of course, this comes back to our friends at OpenAI. Once upon a time formed, it was only 2015, seems so long ago, around the concerns about what Google Brain was doing. That they had hired in Susquevar and Hinton and a bunch of the best and brightest, and were doing stuff behind closed doors. It's like, it should all be out in the public. Do it open. So this was formed by Peter Thiel and Elon Musk and a bunch of other billionaires who didn't actually put any money in, to try and pull all those scientists into an open space, and it kind of unraveled. The first version of GPT came along in 2018, and that was open, but right away it was being abused, because it would write good enough prose that it was great for writing fake news articles. And so when they got to GPT-2 in 2019, they decided to change the model, that just releasing it was a problem, that it was better to control how it was being used. And that was about the time that Microsoft got involved, kicked $1 billion in, moved it all to Azure. And then, of course, by 22, we got ChatGPT, and 100 million users signed up in 2 months. And Everything gets a bit crazy and hairy after that. And now we have the co-pilots. Apparently, last year, Satya told the whole company, here are the OpenAI APIs. Every product team needs to make a co-pilot. And there's like 200 of them running around inside of Microsoft. Hopefully they won't give them all to us. But they're trying to rationalize what they're making there. They're trying to incorporate LLMs all over the place. Microsoft's attempting to lead in the tech space for the first time in a very long time. And we're pretty immersed in a pretty serious hype cycle right now. So it's hard to talk about this rationally. Gartner created the hype cycle term a number of years ago about any technology. Here's the story of it. So you have a technology trigger. Let's face it, language models are not that new, but ChatGPT kind of triggered a bit of crazy. And we went racing up this peak of inflated expectations about how it would do all the things. That seems to be like all of 2023. And I think in 2024, we're right about here. It's just a question of how far down this actually is, the trough of disillusionment. We put unreasonable expectations on technology all of the time. We try to make them do all the things. We don't know if it's right. I often ask the question, because I'm talking about Apple, is it a Newton or is it an iPhone? Same company, same basic concept. In the 90s, they made a productivity device called a Newton that you used a pen on to operate with. They sold about 60,000 of them over 3 years, and then they gave up. And then 10 years later, they made the iPhone and changed the market, right? Once upon a time, phones were kind of cool. They had keyboards and slide-out bits and different antennas. Now it's slab of black glass. Been the same for almost 20 years. Kind of dull, ready to be changed. So all of our tech goes through this process. And so this particular moment, I've been doing versions of this talk for 5 years now, this particular moment, it is hard to be rational about LLMs because we are in this height of a hype cycle right now. But there's clearly some productivity value. GitHub Copilot is the point you can point at and go, but we're using this and it's working. And it can be used in some other places. Power Platform has a Copilot now that allow a domain user to describe a task and have forms, more generated forms, so even more automated. And for those who are concerned about the AI superintelligence, it's not really a thing. That's the science fiction talking. This is the problem working in this space, and if you're going to immerse yourself in it, we now have to be the people that convince the regular humans this isn't actually the path forward. My favorite book on this subject is called Algorithms Are Not Enough by Herbert Roitblatt, who's a real thinker in this space. It just says the generative AI path that we're on does not lead to an intelligence. It has no mechanism for learning from a small number of examples or for identifying specific problems or even setting goals or finding new representations for problems. All things that sentient creatures do, the software has no capability of it. We're just prone to anthropomorphization. We give it more credit than it deserves. It is software. That doesn't mean it isn't valuable. It isn't capable. And again, the noise of the LLM has blinded us a little bit. I would say the single most important machine learning project going on today, right now, making a difference in the world, is from DeepMind. It's AlphaFold 2. This is a tech that is helping to understand protein folding. So there are 10 to the 300th different possible protein folding combinations inside of organic chemistry. They're incredibly complicated to do and to understand. We've been working on this for many years, but in the past few years, we've been trying to do digital representations of protein folding. And the DeepMind folks with their AlphaFold, this is derived from the Alpha product that originally played the game Go. Same guys, video games. Turns out protein folding is kind of a video game. By 2022, they were getting 95% accuracy out of it. It took them longer to validate that the data was correct and the software's ability to compute it. And it's 2024 now. The papers that are coming out of this is just a whole new class of medicines, a whole different way of thinking about how we can keep people healthy and live better lives. And it's not sexy. It's complicated. It's the area of serious scientists. And it was all done open source, so all of them have it and are using it. So it's evolving quickly. Because if we're talking about the software that we normally build, we're looking at a change of UX primarily. We can start contemplating, and we're going to have a panel at the end of the day today talking about a bunch of stuff, so I'm not going to steal too much from, I think, where the direction we're going to go in the panel. But if you really think about changing the user interface, using machine learning, not just the LLM, but machine learning as a whole, that I could recognize the state of mind of the user. Is this person frustrated? Are they flailing around? Could I modify the behavior of my software based on what I saw from the user? Certainly the technology's there. It's just an interesting UX problem. So we have further to go. There's more to be done in that space. And the other moving parts, again, I'm going to swing back to the hardware a bit, open the door to more possibilities here. So what's going to replace the smartphone? The smartphone's won as a client at this point. Figure there's 4 billion of them used on the planet, so pretty much every adult human has one, more or less. A lot of them are just playing Candy Crush on them, but there's a farmer in Uganda with an old-style Android phone who knows when to plant because he's got enough data to have access to a digital almanac and know what the weather's going to be like and say, this is the time. So his crop's not going to fail. And better weather reporting, better communication, the fact that we can communicate with anyone anywhere in the world if you're willing to pay the price. We have the tech for that. But we're pushing against augmented reality. Our friend Tim Cook has gone all in with his $3,500 pair of ski goggles. Lots of people returning them. I asked that question, is this an iPhone or is it a Newton? Because it's hard to know when the tech is right. And so, I'm glad Apple's made this bet, but I haven't bought one. Lots of people have, some people have. And we're still working on a programming model for it. The real question is, what problem space is this addressing? I generally don't find when you look in the past to inform the future, most new technologies find a role in the workplace first before they can really become a consumer product. It's just not that easy to launch a consumer product from scratch, and Apple is kind of a consumer product company. Now, they're not the only ones making headsets. There's lots of them out there. This is what we want Apple to make, except for that part where it's impossible. This is science fiction, too. But you can buy a Qualcomm XR1, which is basically a pair of glasses with earphone, microphone, cameras mounted into it, and tethered to an Android phone, and you're basically doing Android programming for it. So the ability for someone to look at objects and to have information fed to them, that's a $1,000 device. If you want to go a little more Google Glass, that's the Toshiba DynaEdge, again, tethered to a device. And Microsoft's got their HoloLens, which is not actually out of business. They're basically waiting for the hardware to evolve more. They've decided that they're looking for a particular quality of hardware before they go forward on it. We are seeing certain verticals starting to use AR in a meaningful way, so that an operator is able to look through a piece of technology, or a piece of equipment, do maintenance on it, and have a video log of everything they've done and be able to call in help on it. So these are very specific verticals. The problem is the headsets are expensive. They're $3,000, $5,000. It's not just that, it's $1,000 plus per month to run each of those headsets in Azure IoT costs. But we also know the technology will get better. And what we're looking for is, what is the information worker's use case? That's, I think, what's holding AR back more than anything, is what's the use case? Because I'm pretty sure it's not Meta and the Horizon World thing. Zuck renamed his company because he didn't want to focus on advertising anymore. That seemed to be coming apart. He's gone back now. They're back to focusing on advertising. But meantime, he blew $10 billion and made a few headsets and tried to make Horizon World because it was a Teams alternative. Again, I don't think that's the compelling technology. Finding a way for AR devices to really make a difference in our world, that's where you'll see those things take off. But you have to wonder if the combination of this with the machine learning models, creating better UIs, more responsive interfaces, doesn't actually look like a future in the 2030s. That we do wear a screen on our face effectively. It'll be a little svelter, but it's always going to be weird. But once upon a time, walking around with your phone in your hand was weird too. Social norms change when it's compelling enough. It used to be that smartphones were kind of geeky and weird, and I had them, but nobody else did. But most people, when they saw them the first time, did the same thing. I have a Google Glass, same thing. I wore it out. What's the first thing people ask? Can I try it? Put on a HoloLens. Can I try it? If it's compelling, you'll know because they won't give it back. But when it isn't compelling, then they make fun of it. And now you're a glass hole. Like, how did that happen? Social norms will change when the device is sufficiently compelling. So people yell at me about this is too ugly to wear, and it's like, if it was good, you wouldn't care. It's just not good enough. The programming model for this is largely can be done in Unity these days, which is also compelling. Like, we're trying to find better ways to write this software just to make it easier to do. And that, to me, is exciting because it's also part of the challenge. If we're really going to change the user interface, change the client, that's what we're talking about here. We've had PCs, phones and tablets now for more than a decade. They've been pretty consistent. We're ripe for change. What's it going to take? How good does it have to be? What's the advantage? What makes you not care about social norms because the experience is that compelling? What makes you look forward to going to work because you're going to get more done than anybody else because you've gotten good with that set of gear? It's you can smell the shape. All the pieces are there. And we're going to start putting these things together and start to see the next few years what that looks like. And then the rest will thin down. It'll happen in the business place first. It's happening now in the verticals, in the specific industries where they don't care about the cost of it, where the performance advantages are so significant. You look at what Pratt & Whitney was doing with the HoloLens, where they're doing a $5 million service on a $50 million engine. The fact that they spend several $1,000s on headsets, that's fine. Makes perfect sense. But that's not Walmart. That's not everywhere. So first the verticals, then more market spaces. That's going to be a lot of activity, but it just speaks to, it's not going to be in 2 years that we have those in front of us for consumers, but it will be in 10. All right, I'm going to wrap with one fun piece, and that is, because I get asked about it all the time, quantum computing. First off, quantum computing is a class of supercomputing, not a class of general computing. So there's no expectation that we're going to use these machines as our replacement for general computing devices. It's a supercomputing problem space, certain classes of problem. Your usual hype story you will hear in the news is the destruction of encryption. Yes, eventually, someday, quantum computers will be able to break significant RSA-based encryption because it's based on primes. It won't be the first thing they solve, it'll arguably be the last thing they solve. We are already experimenting with non-prime based encryption, so that problem will be sidestepped. It's just that lattice-based encryption is more computationally intensive than prime-based encryption, so we tend to want to use the cheap stuff while we still can. And the only argument is that presumably there are bad guys out there keeping encrypted packets from people they think are interesting so that someday they may be able to unpack them and get value from them. But that's about it. Don't focus on that part. We'll talk about the cool stuff next. We have made real progress. In 2019, Google Sycamore, so this was a 54-qubit computer, although their successful run was 53 qubits because one of the qubits was broken. But they are using superconducting transmon quantum processing, which means this whole thing was soaked in liquid helium to keep it cool enough to actually keep the qubits entangled. They did a computational problem space using quantum random number theory to solve a problem they thought would take 10,000 years with a classic computer. Subsequent optimizations got that down to 2.5 days with a classic computer. But we're still talking, it did it in 200 seconds. So we call that quantum supremacy. The Japanese, their best supercomputer, which is the Taihu Lite, it's no longer number one, I think it's number 2 or number 3, ran the same problem in 300 seconds. So if you get a big enough supercomputer, you can still keep up with these very basic quantum computers. But as soon as that's the argument, this thing's doing something. It was an early stage machine, but it's gotten there. Up in China, they went photonic. So they're actually entangling photons with lasers. And in 2020, they had 113 entangled qubits. They did a boson sampling run, again, 200 seconds, and they figured that one would take about 2.5 billion years on a traditional computer. Nobody's really challenged that, so cool, better. IBM's Eagle and their Transmons designs, they got up to 433 qubits a couple of years ago with the Osprey. And today, just a few weeks ago, they announced the Quantum System 2. We talk about how bad Microsoft names stuff. Because IBM, do you remember DB2? That was really like the second database they made. They just hung on to that name. So yeah, this is the second quantum system they made. There's exactly one of them. Again, runs into liquid helium, uses transmon architecture, 3 Heron processors, and they're looking for workloads. And therein lies one of the problems here, is that there's only so many algorithms that apply in quantum space, and some of them are important, but they're challenging to operate. Quantum chemistry is where we're going to see the first significant impact. So let me tell you the story, and then we'll let you go for the rest of the day. In agriculture, we learned that you can't just keep planting the same crop in the same place year over year, and it keeps growing. It gets worse and worse over time. Stuff we figured out 10,000 years ago in Mesopotamia. You rotate crops. You leave it fallow, or you plant a different crop. Typical rotation was you grow some wheat, then you grow some beans, then you plow the beans under, you let it sit for a year, you can grow wheat again. It works pretty good, right? 3-crop rotation, again, solved in the Assyrian Empire. By World War I, we came up with the Haber-Bosch process, which allowed us to make ammonia, which turns out to make bombs as well as fertilizer. How nice. And so we were able to replenish soils chemically, which we've pretty much done, and arguably is 1% of all energy consumption in the world today, is the creation and distribution of fertilizers. But we had those plants. Remember those plants that we could redo the soils with? The key one was the bean, because the bean has a rhizome on it, and inside that rhizome is a symbiotic bacteria that has an enzyme on it called nitrogenase. So this is how this worked, is this thing grew on the roots of the bean plant. So you plant the beans after the wheat, and then you pick the beans, because that's your food, and then you plow the remains of the plant under, and so all of those rhizomes now decay, and they release the nitrogen back into the soil and rejuvenate it. That's the natural way to go about it. And it all came down to this complex protein, which has been studied for a couple of hundred years, trying to understand how it works. It's a very challenging problem space. And they've gotten down to the point where they understand that there is a catalytic reaction within these proteins between some iron atoms and molybdenum atoms that combines nitrogen and hydrogen. So they take nitrogen out of the air, hydrogen from water, and they make ammonia from it. In a plant. We make factories to do this, but the plant's been doing it for 1 billion years. We just don't understand the catalytic reaction. It's about 140 electrons interacting in that reaction, and that's more computing power than we have on the planet. But a middling quantum computer should be able to crack this in a couple of minutes. Now imagine the consequences. Now, just because you know what the catalytic reaction is doesn't mean you know how to recreate it, but at least you have a guide, a path towards doing that, so that you could do low energy fertilizer production. Now making fertilizer from air and water with a watch battery or a solar panel. That's what quantum chemistry is about. And there's plenty of other cases. Batteries fall into this category. Battery science is largely experimentation. We don't truly understand the interactions. They're too complex. But a quantum computer could probably nail this. And so our batteries, right now we just experiment and try and make better ones, but if we could actually understand the math, we could optimize the battery. Superconductors fall in this category too. We know more about superconductors today, but we really don't understand how that interacts because the quantum interactions are too fast. So there's a set of problems we can work on with quantum computers long before we can crack RSA 4096. The problem is they're all deterministic problems. Once you've solved them, you kind of need to solve them again. And it begs the question, how many quantum computers do we really need? Which reminds me, in history, a guy named Thomas Watson, one of the early chairmen of IBM, when they were going to market with one of their very first mainframes, said, I think there's a market for 5 of these. Now, he was wrong. He didn't actually say this. It was a much more complicated story, but the simplification's funnier. They sold about 20 of them. But they were pretty primitive, right? You're talking about early mainframe computers. And this is the time before the transistor even existed. Part of the challenge was how do you store the bits, right? They were doing the wire coil things, and they used vacuum tubes or relays. The original bug was actually a moth stuck in a relay. was really a bug. And we're thinking about quantum computers and we can't really see, this kind of looks like this, right? They're big bespoke machines. They're unique. And they all have different qubit architectures, just like these things had different bit architectures. This is the first transistor. Pretty, isn't it? It's mostly gallium, or one of the key guys behind this, a very unpleasant human apparently, is a guy named William Shockley. And after he finished at Bell Labs with making this, he set up a company in what would become the Silicon Valley before it was the Silicon Valley. And they were working on the idea of, let's do this with silicon rather than germanium, and can we actually make what would eventually become the integrated circuit? And he was battling with the complexities of the chemistry, and so Shockley actually rented time on an old mechanical mainframe to compute the doping, the best case doping compounds. Should I use boron or phosphorus? Like, what do I dope the silicon with to make these semiconductors? And these old computers helped him enough that he was able to make the first integrated circuits. Shockley then became part of Fairchild Semiconductor, and Noyce and Moore and all those guys left Fairchild to form Intel. It's a straight lineage. So he used the primitive version of computing to build the modern version of the computing that's all of our businesses and all our careers right now. You can't look at this transistor and see this. 25 billion of them, and something that fits in your palm. So I actually don't, we may be in the same situation with quantum computers. So right now we're feeling around for the right way to make a qubit, and we're building these kind of insane, unreliable, bespoke devices soaked in liquid helium. But it might be just enough computing power to design the correct quantum computer that could take us forward from there. And then we might get something like this. Who knows what kind of Candy Crush you could play with that machine. But I do know this much, trying to look forward from here, that we have the very good fortune of being part of this industry where we invent this stuff, that we get to choose what we work on, what we make, and how we make it, take our ethics and morals to it. Try and guide people to do the right thing. You want to know what's next? It's what you make. We make the future. It's up to us. And I hope we do a good job. Thank you for your time. Have a great rest of the day.